Hi folks, I had a query about stopping potential in the context of a Planck's constant experiment. So in this video clip I'll go through what stopping potential means, and I've got a specific question here to look at too. So what do we mean by stopping potential? What I'm going to start with is actually a bit like my video on escape velocity. Imagine this: here you are on the surface of planet Earth and you throw something upwards with some kinetic energy Ek. What happens is that it gets to a particular height and then it falls back down. What we can say about this height that it gets to is that the initial kinetic energy I give it is equal to the gravitational potential energy that it has gained. That is because we're projecting a particle in a field. So the more kinetic energy I give it, the higher it's going to get, because the process here, let's remember what potential means. It's a potential energy per unit, in this case mass. So if I draw lines here, these are lines of equipotential gravitational potential. Any point on this line has the same potential. So any object with mass can move along this line without changing its gravitational potential energy. But as it moves from here to here, it must increase its gravitational potential energy. That is the backdrop to this. The same is also true in an electric field. If I project a charged particle into an electric field in the same way, I'll get the same effect. So let's imagine doing that. Here is an electric field. We're going to create a uniform electric field so that it's similar to the one that we have above the surface of Earth. Obviously, the Earth's gravitational field on a big scale is not uniform, but on a small scale it is. Here near the surface it's uniform. So two parallel conducting plates with a potential difference between them. This is going to produce a nice uniform field. The field lines show the direction of the force on a positive charge. These are supposed to be equally spaced. Again, lines of equipotential would be perfectly horizontal and parallel to these plates. Now let's imagine I take an electron, here it is, and I project it from the bottom here upwards with some kinetic energy Ek. It's going to get to a certain height and then it's going to fall back down again. What can we say about this height that it gets to? We can say that at this height Ek must be equal to the change in potential energy. And the change in potential energy, for a gravitational field, that is the force on it, which is mg times the change in height. No problem. In a electric field, we could do a similar thing. We could do force times distance moved, but probably more useful to say that it is the charge times the change in potential. So when it gets to this point and falls back down again, at this point, if this was an electron, the original kinetic energy that we gave it must be equal to E times the potential difference that it's traveled through. Hopefully that makes sense. Now, let's imagine then, let's go a stage further and say that the total potential difference between my top plate and my bottom plate is V. Ooh. It's kind of done that for me, but is V between the top and the bottom. Let's imagine that I give my electrons some kinetic energy, enough kinetic energy for them to make it the whole way across the gap. Let's say I'm giving some electrons this amount of kinetic energy and they're making it across and they're hitting the other side. What happens if I start increasing V? If I think about this, these electrons are crossing the gap because Ek is greater than EV. What happens when Ek is just about equal to EV? that will mean these electrons slowing down, slowing down, slowing down, slowing down, just make it across the gap and no more. What happens if EK is less than EV? Then the electrons get to here and they fall short and they fall back down again. So 3 slightly different setups, depending on whether the kinetic energy that the electrons have to begin with is less than, greater than, or equal to the charge times that potential difference. Now then, what's this got to do with Planck's constant and stopping potential? Think about this. Here is a surface from which some electrons are going to be ejected with kinetic energy EK. Here is a second surface that they're going to cross this gap and be absorbed onto. If I put these 2 surfaces into a complete circuit, if this process is happening, there must be some sort of current flowing here. To get this process to happen, I have to be giving these electrons some initial kinetic energy. So let's do that via the photoelectric effect. Let's chuck in some photons of energy HF. So long as HF is greater than the amount of energy required to remove these electrons from the surface of the metal, which is phi, then they will leave the surface and they'll jump across this gap. The energy that they've got here, EK, is at most HF minus phi, the energy they've absorbed from the photon minus how much it takes to escape the surface. So I can say that EK is less than or equal to HF minus phi. HF minus phi is the maximum kinetic energy these electrons can have. So let's have a think. I'm shining light on, electrons are bouncing across this gap. What happens then if I introduce that uniform field across the gap like I had before? This side positive, this side negative. Electrons being repelled from up top, attracted back towards the bottom. Let's make V here variable. I can change this, and I'm going to start from 0. What happens to the current that I detect? Now this is a slightly unusual setup. Look, the plus and the minus on my battery pack suggest that I would normally have current flowing this way around the circuit. In this case, I don't. The electrons are actually flowing in this direction, which means the current, weirdly, is going this way. What we're doing here is we're using the energy from these photons to drive electrons around this circuit against this cell or this power supply. So if I start from V equals 0, let's think about what happens. This is the maximum kinetic energy that the electrons can have. Some of them will have less than that. So as I gradually increase V, the ones that have less energy will stop making it across the gap and will fall back down again. Because remember, for them to make it across the gap, we need this to be true. So the ones with the least kinetic energy will stop making it across the gap. As I continue to increase V, more and more of them will stop making it across the gap. And eventually, at the point where EV is equal to EK, equal to HF minus phi, at this point, EV equals HF minus phi. This is the critical point. At that point, electrons, only the most energetic ones, can just make it across the gap and no more. Any more potential difference than that means no further electrons can make it across this gap. So, what does that look like? If I plot the current against the potential difference I'm applying, this is a very strange current versus potential difference graph. What happens is I actually start with a current at 0 volts, because remember, in this case, the potential difference is not providing the energy for the current to flow in this circuit. These photons are. So I start with a current at 0 volts. which steadily declines up to this point. This is the stopping potential. The stopping potential because it's the potential required to stop the current flowing. And it comes about because that is the potential that will provide enough potential energy to these electrons, or rather will take enough energy from these electrons to prevent them crossing the gap. It's the point when this stops being true, and therefore the current stops. Stopping potential. So that's where the phrase comes about from. What has this got to do with Planck's constant? Frequently this is how we measure Planck's constant. What you would do, it's a pretty classical experiment, is you have a collecting plate that you shine photons onto. This is like shaped in some sort of parabolic way or something. So you've got your circuit set up like this. This is a variable potential difference. I don't really know how you draw the sign for that, so I'm going to draw that. It's variable. Looks all right. This is an ammeter. This is sealed inside a glass bulb so that it's a vacuum. You shine in your light. Not red light, that won't work. The electrons are ejected across this gap to here, and you gradually increase V until this current just stops, and you figure out the stopping potential. Then you try a range of different frequencies of light, and you plot stopping potential against frequency. And given that at the stopping potential, I'll put Vs, this must be true. And if I plot stopping potential against frequency, I get a graph with a gradient h, hopefully, and technically I've got an intercept of minus phi somewhere down there. Well, sorry, if I plot stopping potential multiplied by charge on an electron, then I should get something like this. This is the this is the frequency of the light I'm using. Happy days, and this intercept here is the work function divided by, well, yeah, you get it. The work function in electron volts, and the gradient of this is Planck's constant. So that's why this is such a common experiment, a common context for questions and stuff like that. So that is stopping potentials. This was specifically the question that I was asked about. I haven't actually looked at this yet. I'm kind of hoping that what I've just explained possibly explains how to do this question. So explain why current is detected by an ammeter. These photons are causing electrons to be ejected across this gap and therefore flow around the circuit. It's going to be a pretty tiny current. The work function is given. The electrons are emitted with a maximum kinetic energy of 1.2 electron volts. Calculate the frequency. So again, we use the idea that maximum kinetic energy is hf minus phi. And we would get, this is in electron volts, this is given in electron volts. So we'd have to be a bit careful here, and we'd say frequency is that plus that divided by h, and then convert into joules, blah de blah. To modify and use the circuit to measure the stopping potential, what we need to measure the stopping potential, look, this plus minus business here is the wrong way around. We want the field in this region to prevent the electrons from crossing the gap. We want to attract them back to this side, repel them from this side. So this battery pack is back to front. We need to swap that back to front. And that's all we need to do as far as I can see. we've got the ammeter in place, we've got the voltmeter in place so we can measure the stopping potential. So we need to swap the battery pack, and then to use the circuit to measure the stopping potential, we would gradually increase this potential difference from 0, and the stopping potential is the PD required to cause the current to drop to 0. So we gradually increase that PD until the current stops. The metal surface of the photocell is radioactive, emits alpha particles, some of which arrive at the collecting electrode. What effect would this have on measuring the stopping potential, and what could be done to reduce this effect? I mean, you know, don't use a radioactive photocell springs to mind. I mean, who would do that? What metal should we use in this photocell? Oh, I've got some nice uranium here. Will that do? Perfect. Yeah, sorry, that isn't going to help you guys in an exam. Think carefully about this. What is going to be the effect of this? Alpha particles are positively charged, so having alpha particles rock across here with the electrons, you know, that reduces the net current. Current is flow of charge. So if I have like 5, let's go with 10 electrons in a given time frame, that isn't 10, but you get the idea, cross this gap. Well, if there's one alpha particle in the mix with it, the alpha particle at +2, that's 2 less charge crossing the gap. Therefore, there is a net reduction in the current. So those alpha particles, those pesky alpha particles crossing this gap are going to reduce the current overall. And what that means is we'll have a mismeasure. So we'll have an offset, we'll have a mismeasure. Yeah, which is bad times. What could you do to reduce the effect? I mean, well, the straightforward thing to do would be not to shine light on it and measure the current with no light shining on it, because if I take away the light that's shining on it, I remove the photoelectric effect, but the alpha particles will still be crossing the gap. So if I ditch the cell or set this potential difference to 0 and remove the light that's shining on it, then I'll still have alpha particles crossing the gap, and I'll get a current measured here, and all I've got to do is take that into account in all my readings. Right, good. Hopefully that makes sense. This video went on slightly longer than I had planned. I was planning on doing like just a really short video, but I think it's turned out to be quite long. Anyway, hopefully it's helpful. Take it easy, guys. Bye.